Hi guys, it's time to debrief the physics unit. This is where we go back and look at what we've learned so far and how we might be able to apply it to situations that we hadn't been thinking about in the past. So I'm bringing up the balloon car for this so that we can kind of use it as our example of all the physics that we've learned so far. In the beginning, we didn't even know what the word physics meant, and then we defined it as the study of motion. As we moved through the unit, we learned lots of definitions, some formulas, and lots of techniques for modeling motion with graphs and diagrams. The most obvious way to explain motion is to talk about speed, how fast something is going. And we did that in the very beginning. We talked about speed as how fast something's going. And we had a formula. Speed is equal to the distance traveled divided by the time it takes to do the traveling. And that gives you the average speed of an object. And then we added velocity to our vocabulary. Velocity is a little bit different from speed. It also measures how fast, but it measures how fast in a particular direction. And directions on velocity graphs and in formulas with velocity are usually explained using plus and minus signs, but the formula for velocity and speed is the same. You just have to remember that when you write your answer, you have to include the direction. Then we explained something called acceleration. When you accelerate, you do one of three things. You might speed up, that's the most obvious form of accelerating. You could slow down, or you could change direction. So anytime your motion is changing in one of these three ways, you are accelerating. It doesn't have to be that you're speeding up. And we learned a formula for acceleration, and we use this cool little triangle, which is the Greek symbol delta, and it means the change in velocity over time. And you can write that you can figure out your change in velocity by taking your final velocity and subtracting your initial velocity, and then dividing by the time it took you to do that. And we took a quiz on that, and we did some word problems on speed, velocity, and acceleration. Then we moved on to graphing. So we spent a whole week learning how to model motion, and what we did was we would watch a little animation that looked something like this, little car putting to the left, and we learned how to put that into words. So far we've seen the car move to the left, it slowed down, so that was a negative acceleration to the left. Then it was at rest for a little while, and then it had a constant speed to the left. The next thing we learned to do was down at B, we learned how to map this on a time-distance graph. So as time went by, what happened to the distance of the car? Well, in the beginning, the car was slowing down, and you can see that in the shape of the graph. It's curved, and that's because the car's speed is decreasing until it finally flattens out to it's not moving at all.
Its distance isn't changing anymore.
Miss Prati showed up, by the way. Here she is.
Hi, I'm here.
So the distance isn't changing, and that's how you know it's staying still, right? Remember that the faster you're going, the more vertical your line is. And then after that, we had a constant speed, so the line becomes straight. Then on C, we learned how to do time position. And this was tricky because position is different than distance. Distance keeps adding up. No matter what you do, you can't untravel distance. But your position can be towards or away from.
You can backtrack.
You can backtrack, right? Like you can reverse your direction. It just so happens we went in the same direction the whole time with this car, but we were in the left direction. So our whole graph takes place below the x-axis because that's our negative leftward direction. So the car accelerated, had a negative acceleration, and again, it's slowing down to a stop. So it's slowing down to the flat portion of the graph, and then continuing at a constant speed to the left. Then we graphed velocity. And in D, you might have noticed that I had to actually go back and fix this one because I keep forgetting that this one is messed up on your slide. So I changed it so it looks different than it did for the first part of the tutorial. And that's because it's confusing, right? Drawing a velocity graph is confusing because you have to keep track of two things. You have to keep track of how fast you're going and what direction you're moving in. So we had a negative acceleration. So that means we're going to slow down. So to slow down, we have to move towards 0. And we have to decide, are we going to move towards 0 from the bottom up or from the top down? Like we could have come from this direction. But we didn't because we were moving to the left. So we had no choice but to start here and go that way. So we slowed down. Then we stayed at 0, right on the x-axis for a little while. And then we had to go at a constant speed to the left, but in order to do that, first we had to speed up past 0. So we sped up a little, and then we have this flat line, which shows that our speed is staying the same. Because remember, our y-axis now is velocity. So if we have a flat line, that means we're not speeding up or slowing down because we're maintaining the same speed. That's different from on a distance time graph. A flat line means you're standing still because your distance isn't changing over time. And we spend a lot of time on this because it's complicated, and as soon as you walk away from it, you tend to forget it. But I'm just reminding you, we did learn this skill. After we finished modeling motion, we started talking about forces as being the cause of motion, and we defined a force as just a push or a pull. And we talked about the fact that there are only really 4 different types of forces out there in the universe, and we've mostly focused on gravity and electromagnetism. Then we talked about how to make free body diagrams, which are diagrams that show what all the forces that are acting on something are doing. So, for example, with the balloon car, you might have the following forces. You would definitely have gravity, pulling straight down. You would have the normal force of the table, pushing straight up.
This one's on an angle, so it's kind of hard to...
It's kind of hard to draw. I'm going to do the other 2 forces, though, in pink, going back and forth, and I'm going to make the pen a little bigger so it's easier to say, too. So the other 2 forces are interesting. You've got a force in this direction, and you've got a force in this direction.
And that's because of the way the car is tilted in this picture.
Right. It's facing sort of in and out of the screen towards us, pardon the bell. And what are those 2 forces? Well, you've got an applied force that's pushing the car forward. And that applied force is actually from the air coming out of the balloon. And then you have the force of friction on the wheels. And depending on whether or not you have more friction or more applied force, your car may or may not move when you do this. And then we looked at Newton's laws, which have a lot to do with forces. So according to Newton, there are 3 laws that describe motion. The first one is that stuff keeps doing what it was doing before, and that's called the law of inertia. If an object was at rest, it will stay at rest until a force makes it move, and if an object was moving, it'll stay moving until something makes it move or change direction. The second law talks about how if an object has more mass, it requires more force to accelerate it the same amount as, say, an object with less mass. And this came in with our balloon cars quite a bit. And then there's the action-reaction law, which says that forces always happen in pairs. So whenever you have a force acting on an object, that object is exerting a force back on whatever is putting a force on it. So the 2 objects are going to go in opposite directions because they, in a sense, push against each other. So there were lots of examples of that as well in our balloon car lab. And then finally, we've defined the term energy as anything that causes changes in matter. And in the lab that you're doing right now, we've been talking about the difference between kinetic energy, which is the energy of a moving object, or potential energy, which is the energy that is stored in an object before it begins to move. We've been looking specifically at gravitational potential energy, which you measure with this formula. Potential energy is equal to the mass of the object times the gravitational field it's in. On Earth, that's 9.8 meters per second squared. And then multiply that times the height. Kinetic energy is then converted on the way down the coaster. Potential energy is converted into kinetic energy over here. And that formula is, don't you hate it when you do that? That formula is 1/2 the mass of the object times the velocity of that object squared. and we've been working with these formulas quite a bit. Your job with your roller coaster lab was to figure out how to dissipate less energy as your marble travels along this track. And dissipating energy, or dissipated energy, is the energy that is lost or appears to be lost between what you started with, your potential energy, and what you ended with, your kinetic energy. In a perfect world where no energy is ever lost from a system, the amount of potential energy you start with will equal the amount of kinetic energy you end with. But this never happens in reality because in the real world, energy is always leaving the system it's in and moving to the surroundings. And what you had to think about is, where is the energy going that's being wasted? And by wasted, I don't mean being destroyed, because that goes against the law of conservation of energy. I mean, where is the energy moving to? What new forms of energy have we created as that marble rolls down the track? And how can we maybe conserve some of that energy and keep it in the system and on the track so that our marble goes faster? And that's kind of where we've left off. So those are all the things that we've covered so far in our physics unit. We're going to go back and revisit all of those things when we do our final project. And so now is a good time to have an in-class discussion about how to apply all of these things to unique situations that we've encountered along the way. So we'll do that in class together when I see you next. See you guys.